Hi, welcome to this video series on cryptography. Today I'm going to talk about uh, a problem related to computing on the ciphertexts. Okay, so what I mean by that is, suppose you have two sets A and B. Okay, Alice has a set of items, Bob has another set of items. Okay, the question is, can we compute the number of items that are common, okay, between these two sets? Basically set intersection problem. However, we don't want to share the sets, okay, that's the main important thing, okay, without sharing the sets. So Alice will not disclose what are the items she has, Bob will not disclose the items he has, but they together want to figure out how many items are common between the two sets. This problem comes up often in practice. Suppose you have one data set owned by one service, and you have another data set owned by another service, and the goal is to find out some properties, like for example, how many elements are common. How do we do that without sharing the data? Okay, so we have been talking about commutative cipher in this series of talks, and I'm going to apply the idea of commutative cipher using, for example, Pohlig-Hellman cipher algorithm, and show you that this is possible actually. So, using the hardness assumption of a discrete logarithm problem, we can actually do this computation. So the goal is to be able to tell how many elements are common. We will not be able to tell exactly what are the common elements. It's somewhat difficult to do that. We will be only able to say, yeah, we have 5 elements common between these two sets. Okay. We can do more computation than just measuring the number of elements that are common, but for now it's good enough. Okay, so this is basically, you can rename it like private set intersection, if you want to call that way, private set intersection. Okay, so what we are going to do is we have been given two sets, and our goal is to find intersection between these two sets, but without revealing the set elements. Okay, how do we approach this problem? So for that, I actually thought of showing you my Diffie-Hellman key exchange slides, and just will reason about it in a different perspective. Okay, consider this Diffie-Hellman key exchange between Alice and Bob. So we know this picture several times. You have been using this. Alice picks her private key X. Bob does similarly pick his private key Y, and then they compute G power X mod P and G power Y mod P respectively, which is sent across in clear channel as public keys of Alice and Bob. And then Alice takes Bob's public key, writes it to her private key, and Bob does the same, right? This picture is somewhat familiar. We have been seeing this several times. Okay, so let's take a step back and think about this, how we can use this picture for set intersection. Imagine now, instead of G as a generator, what if the message itself is G? Okay, let's assume M is a message, and it happened to be an element of a set Alice has, and also the element of the set Bob has. So how do we now quickly turn this algorithm into finding private set intersection problem? Okay, or solving that problem. So so what happens if both Alice and Bob have the same element M in their sets? We can clearly see that they will both have the same value K here, right? Because of the way exponents work, they both will end up with the same key. That should be not so difficult to see because of the properties of exponent. You have the same. What is B? B is G power Y, and she's applying on top an X, so G power YX. Similarly, A is G power X, and he applies Y on top of it, so they both have G power XY. Okay, so now if we just forget about G, which is a public value anyways, assume G is a message M, okay, private message M. Alice knows it, Bob doesn't know it, but let's assume for a moment M happened to be in the set owned by Alice as well as owned by Bob. So what will happen now? Now the value K that you're seeing will be the same on both sides. So what if, let's say, Bob sends that K, which doesn't happen in regular Diffie-Hellman, but let's assume Bob sends that K over to Alice. Okay, Alice can now quickly compare what she has, right? And if that value is the same as the value that Bob has, she knows that the message M is present on both sides. Okay. Of course, it's trivial when you have only one message. You can confirm for sure that the message M is present in both data set. It becomes interesting when you have multiple messages, right? What if Alice has, say, 10 messages and Bob has 5 messages, okay? And we don't really know what is the overlap between these two message sets, okay? So how do we approach that? It's the similar idea. What we're going to do is, we let Alice first compute the list of ciphertexts for each message in her set and send it to Bob. So Bob will receive bunch of ciphertexts, okay? Each ciphertext corresponds to one message in her set, okay? And Bob will do the same. Bob will compute for each set he has list of ciphertexts and send it to Alice. Alice will take the ciphertext list and apply the same tricks that you're seeing here on her private key. So now Alice is going to have another set of ciphertexts, okay? And so does Bob, okay? So Bob is also having another set of ciphertexts. Now comes the important part. Let's assume we let Bob share his doubly encrypted data to Alice, okay? So why I say double encrypted? Because the first time the message is already encrypted by Alice, and then Bob does it again, right? By rising to power y. So now Bob is going to transfer the double encrypted set to Alice. So what Alice is going to do now is simple. She's going to compute the set intersection. She has already a set of messages here. So she's going to take the set that Bob sent. And if the set has some overlaps, then we know for sure there are some messages that are shared between these two sets. That's basically it. We don't actually know exactly what elements are shared, as long as the number of elements actually is more than one. But if it is also interesting, if one is a subset of another, then we'll also know it, right? Because if say Alice has 3 elements, Bob has 5 elements, and if the intersection has the value 3, then we know for sure all the elements of Alice are present in Bob's set, okay? So there are some more privacy data that may be leaked, but there are a lot of good things you could do by just computing the set intersection of the ciphertexts, okay? That's basically what we are going to do. And the reason why this is working is because of the double encryption preserves the commutative property, right? We talked about commutative cipher. In commutative cipher, the order of the exponent doesn't really matter. And that's exactly the reason why Pohlig-Hellman actually worked. And therefore, we can compute easily the private intersection between the two sets. Okay, that's the core idea. So I'm going to show you my implementation now and demonstrate to you how you could easily compute the intersection between two sets. Okay, all right. Okay, one moment. And now I'm going to do this set intersection in my implementation. Okay, so here is the implementation. We have been seeing this commutative cipher for the last 2 segments or so. I will quickly explain the high level picture. Okay, so nothing has changed. The encryption function remains the same. Remember the encryption function? Basically, we do as simple as this, right? The encryption of a message m is basically m power e mod p. Okay, e is a private exponent, which is basically encryption key, and the decryption is something like this, mod p, right? We don't need a decryption, by the way, for this discussion, so I will not talk about it. So this is basically the encryption. M is the message, E is the encryption key. Okay, so what I'm going to do is basically take the code and explain to you what I added new. So since I need to encrypt a list of messages, I created this enc list routine, which will go through all the message in the message list, right? And keep calling encryption function for each item. So this is basically encryption list. And then I have implemented a little SHA-256 wrapper, which basically takes the list of messages and applies SHA on each of them. Okay, the reason is you don't want to send the plain text as it is, meaning you don't want to send your plain text to your exponent calculation. You can transform your plain text into SHA and then do the encryption, because your message may be much bigger than the size of the group. You know, if you're working with Z star P, so you can apply SHA first. That means you'll get a smaller text, and then you apply your encryption algorithm on that. That's basically what I'm doing. So here is the simple problem now, right? We have Alice who has 1357. By the way, 1357 has no meaning. You can have any meaningful text. And Bob has 3467. So how many elements are common between these two sets? As we can see, element 3 and element 7 are common. So if you run it now, okay, so the program is now running and you get 2 as an output. Okay, so let's add one more just to convince ourselves this is working. Okay, so let's just add 4 here. Okay, this is a set, so we should be able to see 3 elements now. Hopefully this is coming 3. Okay, so you can be sure my algorithm is kind of working. Okay, so I have my Alice set, Bob set. The question is, how do we find the intersection between these two sets without exchanging the actual messages? Okay, so first step Alice does, she computes the hash of all the messages. So basically 1, 3, 5, 7, 4 gets random looking numbers. Similarly, Bob does that. And then the first step is basically for Alice to generate an encryption key. Remember, my commutative cipher actually key generation part generates encryption and decryption. And I'm not interested in decryption key, so I only take the encryption key. That's the little Python syntax to get, if the function returns 2 arguments and you want to only take 1, then you index 0 to get the first return value, which is the encryption key. What Alice is doing is basically, she's using her encryption key to encrypt the list of messages. Okay, that's what she does. And then she sent that to Bob. So Bob has now all the ciphertext from Alice. What does Bob do? Bob similarly generates his own encryption key. And then he also has his own list of messages, right? And he encrypts those messages. Alice now double encrypts whatever messages Bob sent. So here, right? That's what basically Bob does. And then Alice takes Bob's encrypted messages and applies her private key again. Okay, so this is basically double encryption. The second part on the diagram. If you remember the diagram we talked about here, you see here whatever data coming from Bob is encrypted again using Alice's private key. That's what she's doing now. Okay, and similarly, Bob does the same. So Bob takes whatever Alice ciphertexts are and re-encrypts using his private key. Okay, so and now the final step. We let Bob send his double encrypted ciphertext to Alice. We can also actually let Alice compute. Alice do that. Alice send her double encrypted ciphertext to Bob. There are variants, but now I assume Bob can send it to Alice. Okay, so Bob is going to send whatever double encrypted ciphertext he has to Alice. So all Alice does basically is she already has her double encrypted encryption, right? And whatever double encryption Bob sent, and she's basically computing the intersection. And in Python, if you do length, you will get the number of elements in the set. And that's basically what you're seeing is 3. So basically, it's a straightforward application of Pohlig-Hellman key exchange idea together with the notion of the commutative cipher property that allows us to be able to do the set intersection, okay, without revealing the elements of the set. I just wanted you to be convinced that that's the case. I can actually also print, for example, the intersection, okay? So let me make it simple. Let's just create only one common element so we can see the intersection, okay? Intersection will not be showing you 3 or the hash of 3. By the way, if you just exchange a hash, that's not at all private, right? Because other side can compute hash of all the messages and then look at the matching hash, then they know exactly which element is shared. So that's the reason why you don't want to simply share the hash. Okay, that's important for you to know. Okay, anyway, so the hash is not shared directly. The elements of the set are actually not shared. Only the ciphertexts are shared. But together with this notion of commutative cipher, they are able to come up with the count on how many elements are common. Okay, so let's just print this thing. Okay, hopefully we will be seeing only one message. We will not see the actual message itself. We will be seeing one group element because we are doing this computation in group. Okay, as you can see, there's a set here. That means there's a set bracket, which is one element. That's very nice. You have a very good algorithm that will tell you quickly how to find intersection between two sets. The two sets can be owned by 2 different cloud services, for example, right? And they don't need to share the key. They don't need to share the data. They just share the, of course, they need to follow the commutative cipher algorithm, and then they exchange only the ciphers, ciphertexts rather, and in the end they are able to do some computation. For example, how many elements are common. Later I will show you more sophisticated analysis you could do on the ciphertexts. Okay, whatever we did so far is basically computations on ciphertexts. We never shared the plain text directly. So why is this secure? Okay, well, in general, this is secure because breaking this scheme is also equivalent to breaking the discrete logarithm problem, right? Because we assumed that it's difficult to derive the exponent from the public value a and p. In our case, not only the exponent is private, but also the value. Although in this picture G is public, but in my case, I'm actually sending the message, right? Message power X or hash of message power X. So we have private values in both these places, okay? So it's difficult to find the exponent unless you know how to solve the discrete logarithm problem, okay? Well, that is assumed to be hard problem anyways, okay? So that's basically it. So there's a systematic way to compute intersection between the two sets. Now you have to have some trust between the parties, okay? One party can just send malicious data if it wants, so the intersection has become useless, and the other party can start doing some group theory related attacks, okay? So you need to select the good prime. So the prime P that I have selected is basically a safe prime from RFC 7919 to avoid a subgroup containment attacks and that kind of thing. I'm not claiming that I did all the checks here. I just quickly ran through this. I realized that when one of the messages is 1, it's easy to figure out by the attacker that 1 is actually shared. Okay. Anyway, what I'm going to do now is to show you some details related to the encryption list, right? Encryption list is basically a simple wrapper that repeatedly calls the commutative cipher for each message. That's all. And we don't need to worry about decryption because we're not decrypting the message. Okay. So that's basically it. We can quickly compute the set intersection between two sets. Let's see whether here we get 2 elements or not. Yep, here you go, 2 elements. So this works. We can find intersection between 2 sets without sharing the elements of the sets. Okay. All right. That's all. Thank you very much.